In section 9.1, we talked about quadratic graphs and their properties. This video will work problem number 27 from this section's homework. The learning target for this section is I can graph quadratic functions of the form y equals ax squared and y equals ax squared plus c. In this case, we will be graphing a quadratic function of the form y equals ax squared plus c. Now remember your key idea from this section. A quadratic function is a type of nonlinear function that models certain situations where the rate of change is not constant. So in this particular word problem that we're about to talk about, this will graph as a nonlinear function, that is, it's not a straight line, and the reason it's not a straight line is because the rate of change is not constant. The graph of the quadratic function will be symmetric, it will be a curve, and there will be a highest or lowest point corresponding to either a maximum or minimum value. So either one of those two things will exist. Okay, look at the problem. A bird drops a stick to the ground from a height of 80 feet. The function h equals negative 16t squared plus 80 gives the stick's approximate height h above the ground in feet after t seconds. We will graph the function and then we'll figure out at about what time does the stick hit the ground. Okay, so notice that I have a diagram of the situation, which is a bird in a tree. And according to the problem, the bird drops a stick to the ground from a height of 80 feet. So in our case, that means that from where the bird is to the ground is a distance of 80 feet. And the bird is going to drop a stick. So what we really want to know is, well, what time does a stick hit the ground? Now remember that these functions, whenever you drop something, gravity plays a role in this. And because gravity plays a role in the speed of the object as it goes toward the ground, the speed of the object is not going to be constant. So what that means is that you're not going to get a linear graph, you're going to get a quadratic graph, a curve. So in other words, after about a second, the stick is going to be somewhere in here. Maybe after about 2 seconds, it's going to be closer to the ground and then it's going to hit the ground. But notice that in the first second, the stick is not going to fall as far as it does in the second second. This is what creates that quadratic curve. Okay, so let's graph this. Again, we're looking at what we call a one-quadrant graph because everything is positive. Time is going to be our x-axis. Height is going to be our y-axis. So we're going to go ahead and label those. Okay. Is going to be at a maximum of 80 feet. So I'm going to go ahead and use a scale of 10 along my h-axis. So 10, 20, 30, 40, 50, 60, 70, 80. And the stick at 0 seconds is going to be at 80 feet. Now as far as time goes, this particular problem, it is going to take between 2 and 3 seconds for the stick to hit the ground. So I'm going to show you why that's true as we go through the problem. So let's pull some points out of this. So I'm going to draw a t-table, and my variables are t and h. And when t is equal to 0, I know that I have a height of 80 feet. You could either reason that out because of the problem, or you could, within the function h equals negative 16t squared plus 80, evaluate that function for t equals 0. And if t equals 0, negative 16 times 0 squared is 0, and 0 plus 80 is 80. Now at 1 second, that means that I'm going to evaluate this function for 1. So evaluating a function, we use function notation. So I'm going to say h of 1 is equal to negative 16 times 1 squared plus 80. Well, that's negative 16 plus 80, and negative 16 plus 80 is 64. So in the first second, the stick is going to drop 16 feet. So I'm going to go ahead and graph that in the first second, so we'll put the first second here, the stick is going to drop to a height of 64 feet. So if I've got 10, 20, 30, 40, 50, 60 is, so 64 would be about right there. Okay. Now let's figure out where is the stick after 2 seconds? So again, I'm going to evaluate this for a t equals 2 value. So negative 16 times 2 squared plus 80. Well, 2 squared is 4. Negative 16 times 4 is negative 48. And negative 48 plus 80 is 32. So that would be at 32 feet. So notice that at 2 seconds, so this is 1, now this is 2. At 2 seconds, I'm going to be at 32 feet, which is about right here. So notice that it dropped more. The stick dropped more from 1 to 2 seconds than it did from 0 to 1 second. Okay, so let's try 3. And again, we're evaluating the function. So h of 3 is equal to negative 16 times 3 squared plus 80. Negative 16 times 3 squared would be negative 16 times 9 plus 80. And if you type that into your calculator, you're going to get a value of negative 64. So that means that over the next second, we're going to actually be below the ground, which doesn't really exist, but I'm going to graph it anyway. And it's going to be about negative 64, so it's going to be all the way down here. Now remember, we're strictly dealing with positives in this situation. So really when I graph this, I'm only going to graph the positive. So let's draw a graph, the curve, and the curve is going to look something like this. Okay, and it's just going to keep on dropping down. So where would it be, about how many seconds does it take it for it to hit the ground? Well, you can look at that and you can get a pretty good estimate. The estimate is going to be right at around 2.3 seconds. Now remember, from the graph we can get an estimate, but there is a way that we can mathematically calculate the amount of time that it takes for this particular stick to hit the ground. And that's what I'm about to do. So again, my function is h equals negative 16 t squared plus 80. And negative 16 t squared plus 80, I'm wanting to know, well, when is the height of the stick going to be 0? Because a height of 0 is ground level. So I'm going to replace height with 0. Then I'm going to subtract 80 from both sides. So that gives me negative 80 is equal to negative 16 t squared. Then I divide both sides by negative 16. T squared then is equal to 5. And then if I take the square root of both sides, t would be approximately, and then I want to put the square root of 5 into my calculator, and it's about 2.2. Okay, so it takes about 2.2 seconds for the stick to hit the ground. And if you think about it, that makes sense, because the graph did indeed show that the stick was hitting the ground at around 2.2 seconds. Okay, so let's write this in a complete statement. So the stick will hit the ground in approximately 2.2 seconds.